Thank you very much, Ramon, and thanks everybody, especially to this wonderful team here in Salamanca for the invitation. Could you hear me? Okay, fantastic. It's better because I have more freedom to move. Okay, first of all, I have less than 20 minutes, so I try to convince you about this topic that is a relatively new topic. But my idea, more than talking about predictive control, is in general talking about control and evolutionary game theory, something that, according to our experience, so far is not extremely well known within our community of control. So I want to introduce this relationship between game theory and control, talking about several partners or several groups of partners in the world, and how they have this relationship. Different people, different topics, different scenes. So I want to try to relate control and games towards the solution of problems that exist in common frameworks within the main goal of solving, in a clever way, the control problem in this plant-wide control. Well, so there are three objectives, main objectives of this short talk, that are explore the complementarity of well-known fields dancing together. Okay, some people know perfectly how game theory works. Some other people, as you, know how control works and within certain frameworks. But my idea is try to connect both fields within a common, trying to have a common framework. The second objective is solve or trying to, at least, new challenges raised by modern statements of real systems. For instance, this very sexy topic about plant-wide control. The third is show preliminary ideas. I should highlight this part, preliminary ideas about this combination, this new combination, this new framework we are trying to explore and how it works within our framework as well. And of course, this is a very important objective for today. Okay. Well, so having this in mind, the context of the talk is more or less give you some basic concepts about game theory and the context of game theory, the attractive context for us as control engineers or control-related people, then showing or highlighting these bridges, these links among the game theory and control problems. Remember that my sentence or my phrase was dancing together, right? So talking about some control topologies, interesting control topologies for our approaches and ways of interaction between them, among them. And some first steps, like it's a bit of advertisement about our activity, our results so far. Well, so in order to give you a very brief history about the context of game theory, I should comment about two big branches in this area that are the cooperative and non-cooperative games. And each of these branches has like a star. The first one is this guy Chapley that proposed a power index in order to know, given a player with a strategy and all the theory. I don't want to be focused on the basic concepts about the theory, but believe me, how relevant a player is. I mean, the game theory talks about how different players, some people call agents, but let's say players in this case, how they, or what is the relevance of each player among community. And this power index gives us the utility according to the player's distribution. On the other way, we can see this guy, very clever guy, that is John Nash, and he proposed many years ago, and notice the extension of his article, beautiful, the theory about the Nash equilibria, and how the Nash equilibria, or how the distribution or the situation of the players that they are together in a population, how they can obtain some benefits, but without surpassing the benefits of other agents, of other individuals or players. So therefore, having this framework in mind, we are focused on this part of games. This part of games that are the non-cooperative games. Why? We will see later, a little bit later on. And within this family, we can find the matrix games, the continuous games, and for us, something that we were exploring, and this is interesting for us, you will see the interaction or the relationship between some terms, some concepts with us, with our control community, that are dynamic games. Why? Because these guys, these Maynard and George Price, proposed the way of each player evolves toward having the benefit, but all players should converge towards the same benefit. So the competencies is in a specific framework, but in a way that you can describe this evolution by using the equations, dynamical equations, and then you can connect this evolution with the concept of the equilibrium, or the equilibrium, the Nash equilibrium. So all players should reach the same point, and if they respect the way they evolve and they reach this point, we can start talking about the stability of these dynamics. Therefore, notice that we here we doing some a little bit of history. We start identify some connections with our theory. Then, within this family, we can state different way players interact among them. For instance, if I don't want to get into the details about the different families within the dynamic games, but each player has like chooses a strategy to play, the player, in order to get the benefit. So the evolution towards this benefit, and given that they should reach the same benefit, determines this point. At this point is like an optimal solution of a problem, an optimization problem. In that case, is a Nash equilibrium. When we cut this domain, domain is called the simplex, and it corresponds to the domain of these guys evolving towards the same benefit, we can cut this curve, or we can project this curve in an n-dimensional space, and it could be demonstrated, not here, that this evolution corresponds to a maximum of a concave function. So concepts about optimization and the way it is stated start to be quite clear in order to connect our optimization procedures with the way the evolutionary game theory, or at least these dynamic population games work. Well, by the way, I have some references in such, in case you are interested in knowing more. Another concept that rises from this theory is the fact that when you have different players, they can choose a strategy to play, but depending on the way these strategies are distributed, they need to interact each other. So when you have the interaction, full interaction between players, you are stating a problem with no constraints. Let's say no constraints because they can communicate each other. But when you have different situation in the distribution of strategies, you start having some conditions in order to share information. So they need to find a Nash equilibrium under distributed information sharing graphs. Notice that here, if we start relating our theory with this theory, this guy needs information from this, but this information should be connected through this other guy. Therefore, given that they should reach, or they must reach the Nash equilibrium, in this case, they should start interact together, all together. Therefore, we can start breathing the concept of distributed control. Well, why? Because in this theory, according to some of the bibliography and some of our preliminary works, or preliminary works of my colleagues, in this case, Professor Nicanor Quijano from Andes University in Colombia as well, they state some concepts about the distributed population dynamics and how they interact each other, taking into account the way they choose the strategies to play and the way these strategies are distributed as well. Well, but then we can also prove, no here, I repeat, the relation that exists between the Nash equilibrium and the wave on and the KKT, the Karas-Kuntuner conditions in the optimization problem. Because under some conditions, this Nash equilibrium satisfies these conditions. Therefore, you can state an optimization problem taking into account the description of these dynamics that you are considering in the way of how the the players evolve with an optimization problem. In that case, is the maximization, because all players should reach this Nash equilibrium. So you need to find this Nash equilibrium, and it corresponds to maximizing this space, so to find this point along this domain. Notice here that given that we are playing with players satisfying some constraints, they have like a resource. This theory is quite close to the theory of animals in a competition for food. So in that case, the food is constant, or is limited, and the population should satisfy the constraint of the amount of this food, of this resource, should be finite and should cover the necessity of all players. Therefore, you can state this optimization problem and start relating the solution of optimization problems by using this theory. Well, okay, and from this part, a natural problem of resource allocation cases rises in the sense that I have a control objective having this optimization problem. I have this resource delimitation and the amount of resource assigned per each player, and then I have the positiveness of this resource. I mean, there couldn't be in some statements a negative amount of resource. Notice that the resource could be anything I want, and here a concept of flow-based systems could appear as well. Notice that having these other concepts could be related as also with our theory, that is the case of stability. It could be demonstrated that some of these functions representing the fitness of the players within the strategy, or having the strategy within the population, are Lyapunov functions. Therefore, we can study the stability as in the classical theory. Well, having this statement, this framework in mind, what we have tried to do is applying all this theory, all this way of solving the problems we have in general in our everyday activities in control, towards the solution of different kind of problems. In that case, what the first thing we tried to do was attacking the formation control, the well-known formation control, respecting these constraints of proximity and sharing of information, towards having certain formations and towards having the possibility of integrating new players, or new, in this case, UAVs, in the formation in an automatic way, solving a well-known problem of optimization and having a proper performance. What we did was stating a strategy, of course, in this hierarchy, or in this distribution of responsibilities within the statement or a control problem. And now what we proposed was designing a strategy for supervision, such that all the followers following a leader can follow the leader, but without needing without the necessity of knowing where the leader is, just knowing where is the neighbor. And then, knowing the position of the neighbor, I can maintain my position with the deformation that is imposed, but in a distributed way of controlling the requested signal. In this case, we have, okay, oops, we have different cases where we change the deformation. I don't want to extend because the time is gold. And in this case, we have integrated a new member into the formation, and we preserve the formation. And here we have changed the formation in a specific time instant. Perhaps there's no time to show the video because it's not. It's just simulation. This video and this activity was developed with people in Argentina, in Instituto Tecnológico de Buenos Aires. Professor Ricardo Sánchez Peña was working with UAVs, and we developed the real experiments with real UAVs, and seems things work properly. But however, we are interested on more bigger systems, and we were focused on working on this kind of system, large-scale system. I want to point out that for us, large-scale systems are not only networked systems, but could be interpreted as systems with high-dimensional feature. Therefore, evoking your presentation about the way of partitioning the dynamics of a system, we can also introduce this concept within this framework, right? But as you may know, you can have a system and you can determine, magically so far, the way of splitting the system into subsystems. And then you have several possibilities of interacting with the subsystems. The first one is a possibility of having local controllers, and you are in the particular family of non-centralized controllers that is called decentralized controller. However, the coupling is here, but not here. Then you can consider coupling here if you don't consider you are in the decentralized case. But if you start considering this coupling, you have distributed schemes where you could have information or sharing the information in a parallel way and in a serial way. If you remember the condition I showed beforehand about the constraints of each player within a graph, we can interpolate this concept to this framework as well. Therefore, our new new goal was trying to attack the topic of distributed control by using game theory, taking into account the condition discussed before. Allows to model the interaction of the distributed decision makers or local controllers once you determine how to split the system. Notice that according to the formulation stated so far, we have this coupling constraint, but it's a unique coupling constraint. I am supposing that I have a resource and I need to manage the resource properly such that this problem has solution, and the solution was treated in a distributed way. Therefore, the first step is determining among a system with the several subsystems how these subsystems should be connected. That's why we towards always the distributed optimization-based controllers implementations. So what we did was taking this well-known for us benchmark, let's say benchmark that it consists in the aggregate model of Barcelona water supply network, that is a flow-based network of large-scale nature, like let's say large scale, but this system only has 18 states and 61 control actions. I mean, with respect to the biggest, is moderate. But what we wanted to determine, unfortunately, is not properly seen, the different relation among the possible dynamics here. And we relate the dynamics inside the network with these players. And we need to understand how these players interact among them. And then with analyzing this interaction, I can determine a previous or preliminary partitioning in order to design afterwards controllers for each one of them, taking into account the interactions, of course. But notice that the interactions or the amount of interactions is high. So we move on and we determine the way of this constraint regarding the this coupling constraint regarding the resource allocation, how can we split or how can we integrate more conditions, more coupling constraints, each one for each subsystem, such that we can implement distributed or local controllers per each one of the determinant or the stated partitions or subsystems. In that way, what we want to reach is the goal of having multiple coupled constraints and designing, or in the process of determining this, we realized that we could implement the controller by using this kind of population games, the density-dependent population games, well known in biological systems, but not in control systems. So that's why I insist in telling you, that this preliminary exploration is full of surprises also for us, because we start importing several concepts from other disciplines, and we start integrating them and trying to know whether or not they work properly for our purposes. Then we design this strategy with a general scheme that I don't have time enough to mention, but what we realized that we could implement the distributed MPC, let's say distributed MPC or distributed optimization-based controller, stating the constraints, the optimization problem by using this kind of dynamics, solving the problem, or again taking into account our, let's say, benchmark of battle horse for working in these topics, that has this problem, this optimization problem, different control objectives, this objective talking about the smoothing of control actions, following a reference that this is not fully true in our case, but is the way of showing this result, and penalizing an economic objective of the functioning of the system, subject to, of course, a model, a flow-based model with disturbances, and a domain of operation or constraints, operational and physical constraints. And notice that given that the network has not only dynamics but some static relations in nodes, merging and splitting flows, we need to include several equality constraints as well. Therefore, we realized that we had different interaction among players within the system, and this interaction varies along the time. And for us, it was important because the amount of links among the system players was reduced after the first iteration. Something that for us is nice because we can reduce the computational burden, attacking the design of the distributed MPC controller. Something that is nice, fulfilling the control objective, reaching the control objective, fulfilling the constraints, taking into account that the disturbances are periodic, they have periodicity. Therefore, we need to reject this periodicity in the regulation, for instance, in this case, of the volume of the tanks for water distribution. Here, it's important to say that we compare, of course, in simulation, because we don't have a network at home, this comparison between the distributed MPC controller based on this density-dependent population dynamics with the centralized MPC, and our result was the same in the sense of the performance of the control. But the number of links was reduced, and if we relate like a cost with every single link, we can reduce the costs of implementing an DMPC with respect to a C centralized MPC. But not only for designing the control itself, we can show the usefulness of evolutionary game theory or game theory in general. We can not only design the controller, but also help the controller to do some task or to complement the controller. My first question when I started my PhD thesis working in MPC was, how the hell you can determine the weights for tuning this multi-objective optimization problem? So, given this question, old question, and perhaps is an old question into the framework, we explore the possibility of saying to the game theory or the game strategy, okay, let's tune the system automatically, taking into account that you have disturbances. Of course, if you can determine offline a tuning, a suitable tuning, it's okay, but because okay, the nominal behavior is determined, and you tune, and that's it. But when you have this constraint, hey, shut up. These disturbances, things are different. Therefore, we propose a dynamical tuning based on games, and what we had was the same battle horse with different disturbances. Notice that disturbances are periodic, and we change the disturbances and at a certain time instant along the simulation scenario. And from all these plots, what is interesting was that the weights, the behavior of the individuals within the game theory approach was adapted such that the tuning was proper, always taking into account that I have chosen a management region within the Pareto front of this multi-objective optimization such that I know that if the system evolves within this management region, the performance of the closed loop is, for me, acceptable, or for me, is the performance I want. Well, for both scenarios, changing the disturbances, the adaptation of these players was proper, such that we fulfill the performance of the closed loop, and the tuning was properly computed. The nicest thing for us was knowing that with respect to static tuning, this dynamic tuning represented for us this improvement in the closed loop operation. Of course, numbers that do not say something clear, but for us, an extraofficial information from the Barcelona water distribution system is that per day they spend more or less 70,000 euros in electricity, right? Having this dynamic tuning, we can save 1 day of economic expenses for electricity per week, something that is an advantage for this kind of operation of this large-scale system. Well, that's over for so far. But my idea was, again, showing you the interaction between concepts in game theory, something that is related to dynamic games, and the problems we have solving optimization problems, and in the design of the optimization-based controllers. This exploration of possibilities is ongoing, is an ongoing task. For us, it's nice because the implementation of the game theory approaches is relatively easy in the sense of the formalism of the theory and the implementation in code. And we are working towards exploring new fields. In fact, this is for us one of the main topics for research with Wichak, that is a PhD student in our group. And of course, trying to implement this approach in a device for real-time operation, given the facility of computation and the savings, not only in time, but also in the savings that it represents in the performance of the system. Well, ongoing research, and in order to know more, fortunately for us, we have a special issue in the Control Systems magazine talking about this field, trying to break in the ice of game theory, game theoretical methods and control in engineering systems. I invite you to have a look. We have 4 large papers from mainly Professor Frank Liu is here in this paper. Here, people from Seville, Philly, Pepe, Eduardo, our team working on exploring these possibilities. That is an heterogeneous team in UPC and Bogota in Universidad de los Andes. And Professor Jason Marden, that was a student from Jeff Chama, exploring the part of robust social influences, talking about game theory. Well, that's over. Thank you very much for attending, and I hope that for you this new topic was interesting.